Alright, in this video here we're going to look at one more surface of revolution, and this particular problem has been rigged so that the stuff under the radical in the surface area formula will form a perfect square, which will offset the square root, and so that we can do integration here. So we're going to go ahead and look at this 1 plus the 6 x to the minus 1/2 minus 3/2 x to the 1/2 quantity squared. Then we'll go ahead and FOIL that out. So that'll be 1 plus 1 over x, 1 over 36 x to the minus 1 minus 1/2, and then plus 9 over 4 x. And what we'll do is we'll rewrite this as 1 over 36 x to the minus 1 plus 1/2 plus 9 over 4 x to the first power, and this is actually a perfect square trinomial, so we can go ahead and factor it, and it'll be 1 6 x to the minus 1/2 plus 3 over 2 x to the positive 1/2. And you can you can FOIL this out here and verify that is the case. So again, this particular problem is specially rigged so that we can find the surface of revolution. Okay, so what we're going to look at here is something like this, and we're going to go ahead and revolve this around the x-axis. So we're going to revolve around the x-axis. So the height of this function, or the r of x in the surface revolution formula, is just going to be the function here. So we'll go ahead and write in the function here. It's 1/3 x to the 1/2 minus x to the 3/2, and then we're going to do it on the closed interval 0 to 3. This is going to be continuous enough here on the open interval here. So let's go ahead and take the derivative, and we'll go ahead and put this into our surface of revolution formula. And on that previous slide, we're going to be working with that integrand. So here we go ahead and put in our radius, or distance from our function to the axis of rotation, which is just the function this time. And then we got this stuff going on in the radicand here, and that's what we worked out on the previous slide. Okay, so we'll go through the motions here, and we'll see what we got going on here. So we got 1/6 x to the minus 1/2 plus 3/2 x to the 1/2 quantity squared, and then the square root's going to undo that. So we'll undo that, and then we'll do a little bit of factoring, and then we'll expand it out, and then use the power rule to integrate everything. Okay, so we'll rewrite what we had on the previous slide there. Okay, and out of the first parentheses, we're going to factor out a 1/3. In the well, I guess I do that in the next part. Let's see. Okay, so we're just having the square root and the square undo each other. Now what we'll do is we'll factor out a 1/3 out of the first parentheses, and that'll give us x to the 1/2, and then minus 3x to the 3/2. And the second parentheses will factor out a 1/6. When we do that, it becomes x to the minus 1/2 plus 9x to the 1/2 dx. And then what we'll do is we'll pull out the 1/3 and times the 1/6, which is a 1 over 18, and then combine that with the 2 pi, which will reduce to pi over 9. And then we can go ahead and multiply. So we got x to the 1/2 times x to the minus 1/2. That'll be just 1. X to the 1/2 times 9x to the 1/2 will be 9x. Minus 3x to the 3/2 times x to the minus 1/2 will be minus 3x, and then minus 3x to the 3/2 times 9x to the 1/2 will give us minus 27x squared dx. We'll go ahead and do our routine integration. So we have x plus 3x squared minus 9x cubed, and then we'll go ahead and evaluate that, and You can do that on your own time, but you'll end up getting pi over 27. Okay. So probably the big challenge of this problem is on that first slide where we have to work the integrand to get something that's a perfect square, so we can get it out of the square root so that we can integrate it. Again, what I've mentioned on other arc length problems and surface revolution types of problems, you know, if you just say some random function you want to find the surface of revolution, it may be fairly difficult to integrate it, and you probably need some sort of technology or numerical integration to actually find that surface of revolution. Wolfram Alpha does a good job of doing that. Alright, but this is an example of something that we can actually handle using a little bit of algebra and integrating it by hand.